Welcome to this third lecture in this course on quantum mechanics. In the first two lectures, I presented a scheme of quantum mechanics which finished at predicting a thing called probability. And that means a test of that scheme would be, experimental test would be, that we measure probability. In a sophisticated experiment, measurement is needed to decide between quantum mechanics and classical mechanics, that which is the better or which is the right theory. Now that is done in the next lecture, next video. But in that experimental testing of probability and quantum mechanics, you have to pay attention to two things. One are in sophisticated experiment, there are controlled conditions, and you have to understand conditions, and then you have to also learn how to experimentally recognize probability. So I think it's better that you do not take two complications together. In this lecture, you do not have to pay attention to what are controlled condition understanding. Rather, just take a simple observation. Rather, that means in a room, in your room, light. That's it. For that, you should learn in that simple conditions how to recognize probability, and then you combine your understanding of probability, which should be in this lecture, how to measure. Then you combine in the next lecture with control condition. So in this lecture, the topic is how to measure probability. You have to understand that much, and for that simple situation is light in your room. That's a natural condition. You don't need to understand any artificial condition. The simple situation, you should make a discussion somewhere logical only. And logical only is for this third question, that what kind of light would refute. It's not actual experiment. If that kind of light would refute quantum mechanics. The purpose here is just to recognize probability and check your understanding of probability. If you understand probability, you should be able to answer this question: if that were the case, what would happen? If that were the case, what would happen? Make sure you understand probability well, and then you should be able to understand the deciding experiment in the next lecture. So the first is only how to recognize probability, and that is this lecture. Now probability, if I understand, I think you can start in a simple situation, maybe the simplest of all probability experiments, and that is just a coin. First, immediately emphasize it that the topic is here the measure probability, not calculate probability. Someone can say that those who do not understand, they may think, what I'm saying is only that if you have two sides, then you divide 1 by 2 and you get probability, and that is calculating. That's not measurement. So measurement is what you see. That thing 1 by 2, you don't see by your eyes. What you see your eye, what you can see is that if you toss, then you, as is tradition in English, you or whatever, you choose one side, you call it tail, and decide, you label the other side as head, and you know what is tail, what you have decided. Then just count how many heads are there. Initially, there's no pattern. One time you do it 10 times, one set of 10 times, you met 6 heads, so the head fraction is 6 by 10, which is 0.6. Next time you repeat the set, you 10 times repeat, and you make a summary of the data, and there's nothing. There's no pattern. It could be anything, almost anything. It may be as far as 0.2. Next time you repeat 10 and then conclude, and your conclusion could be maybe 0.7. I don't know. So initially there's no pattern. So then you think, what is the use of this? Can you see that? Is that science or is it just a mathematics? The answer is a claim, and in physics is a lesson of physics. I don't have time to explain why this lesson is there, but you have to. I tell you a way, but that's for only those who understand computer science. But those who do not understand computer science programming, to them, I clarify that I do not mean that large number of times that you take a coin and you toss thousands of times. That's very impractical. So how this is justified in a physics course, statistical physics course, I don't have time. But just tell you the result which is taught in physics. This is not quantum mechanics. This is already statistical physics, if not statistics course as well, is taught. And that is that if you repeat a large number of times, you don't make 10 tosses, you do 10,000 tosses. And then the ratio of one side would be almost 5,000 divided by 10,000. One side will appear almost, it's not exactly 5,000. It will be 5,100 something, 122. And there would be accordingly. And then you repeat it, would be 4,900. It is, and divide totally 10,000. The ratio will approach 1 by 2. Now that, I don't have time to give you any reason for that, but those who know computer programming, to them I show a way to verify that can be done. But if you, in computer science it is called loop, and in a loop you give a command something like 10,000, and inside a loop you have a random, that means you just generate 0 and 1. I don't have more time on that because not everyone knows this computer programming. So I just suggest that those who know computer programming, for those who understand what I said about loop and random, they should pause the slide and read this, and I hope that will be simple for them. But I do not take time of others who do not have computer science. They have to just know that this is a result in physics. Historically, there are other reasons as well before emergence of computer, but sorry, I don't have time to tell you the reason for that, but you have to remember the result. So I skip that. You can pause, and I go to, in speaking, I go to the next slide. I start using it, and using this result in this way, that you learn what is the lesson, what is the relation between probability and what we see. I start with the case of toss. What happens is, the number of times one side appears divided by total number of tosses for a large number of tosses. I said something like 10,000, and here approximately 5,000. The ratio becomes approaching to 0.5, 1 by 2, which is theoretical statistics result, mathematical result. And that's not about toss only, that is any number of possibilities. The ratio of appearance of one possibility divided by total number of experiments, that approaches the probability. So that is a very crucial result, and to emphasize that, I've made it in a box that experimentally visible. I emphasize it's not calculational. I mean what you can see your eyes probability, and that is you see that number is proportional to probability. The number is what? Number of appearance. But main thing, you have to memorize it, try to do it. I will not have time to show it again and again along with the detail, but you remember the result, and I repeat it again. The number of appearance is proportional to probability. That is if a large number is there. But if a smaller number, as I said, 10 coins, no pattern. So this combination is necessary. If it is always 1 by 2, it must be a mathematical rule, not probability. But if it is combination is there, for large number is a number is proportional to probability. That's the main lesson. For small number, no pattern. These two conditions make you seeing probability by your eyes. And that is must be somewhere in science. And quantum mechanics is a science. Eventually. Now I think I apply the probability to, as I promised, a simple observation, which is physics, which is related to quantum mechanics eventually. Coin is not that much related to quantum mechanics, but here it's same lesson, but in another situation. That is a room, somewhere you have brightness, some you have darkness. Now, 19th century, the physics before quantum mechanics said that there is electric field and magnetic field, there is a calculational, and their square summed with sum to each other, electric field square plus magnetic field square, that is proportional to energy density. So if you have a large energy density, classical mechanics, 19th century physics said that here there is a large values of electric and magnetic fields. You take it this way or this way. That was classical mechanics before quantum mechanics. Now quantum mechanics replace energy density with, electric field is, as I said in the last lecture, electric field is a solution of wave equation, Maxwell wave equation, and that is wave function. And wave function square is proportional to quantum mechanics is not energy. Quantum mechanics is probability. So here classical says energy and quantum mechanics probability. Is that a mismatch? The answer is not. Reason is the following. That here the number of detection is large because you can't see photon, but you can calculate. Per unit time you have a 1 watt of energy, that means 1 joule per second, and if you have 1 photon has energy of 1 electron volt, then the number of 1 electron volt is 1.6 10 minus 19 joule. Joule cancel, units cancel, and you are dividing by 10 minus 19 almost, and the result is 10 plus 19. It's a million billion multiplied with 10. So that's a huge number. As I said, number proportion become proportional to probability. But so the probability, which is quantum mechanics new result, that becomes equal to number, and number you multiply with the energy of 1 dot, and that is the total energy. So the net result becomes energy density. So energy density, classical mechanics, quantum mechanics also becomes energy density. So both agree. Okay? So at most you can say that this says that quantum mechanics is not against observation, but that is not a deciding experiment. So purpose has been more your understanding. And I summarize it, that visible sign of probability is that for a large number you see a pattern, and for a small number you see no pattern. So now in the part of the course is that now we have to start comparing classical mechanics and quantum mechanics. So far there was total agreement. Now, is there any difference? No. In this lecture remaining time, there is only logical discussion, not any actual experiment. That what you learn, what would be difference, and for that, if the number of dots is small, how it could be small, that's the next lecture, next video topic. Furthermore, just learn. If the number would be small, classical mechanics would say a pattern. But quantum mechanics will say no pattern. So for small number, how to get small number, that's a separate topic. But furthermore, just learn. If it is a small number, that will distinguish between quantum mechanics here and classical mechanics here. Now, if you want to do in our world, and I tell you next time what we mean by our world. In our world, experimentally, you have to reduce the number of photons, and I don't have time to go back to photon calculation. You better remember what I showed. Those 1 joule divided by photon energy. But if you want to decrease it to something like 10, you have to decrease 1 joule numerator energy by a million or billion times less. That was achieved in technology, but that is a topic of next video, next lecture. In this lecture, before concluding, and concluding would be again a summary of what I have been repeating, I have to tell you what was the top announced topic of this lecture, this video, and that was that could your room light refute quantum mechanics? It's just a logical question, just for understanding, and the answer would be that here I am repeating how to recognize probability, that a fixed pattern for a large number pattern, and that are not written. The main thing is for small number, if a small number, quantum mechanics says no pattern. But if a small number, even if for small number, if you see pattern in room light, that would refute quantum mechanics. Now, in our world, and I know I'll tell you again, and I am using the word our world. In our world, how to do that? That's the next video, next lecture topic. But here I'm not talking about our world. It's just for your understanding. I am posing a if, and the purpose here is educational. You must be able to answer a question. If someone asks you, no, it's not necessary that you understand why the question is asked. But if you have any understanding, you must be able to answer this if question. That if Planck's constant were large enough, so that if Planck's constant is doubled, the energy of photon doubled, and if Planck's constant becomes a million billion times more, then photon energy would be, rather than 1 electron volt, 10 to the 18 electron volt. Now, electron volt is of the order of 10 to the minus 19, 10 to the minus 19 multiplied by 10 plus 18, 10 to the minus 1, divide by it, you will already cancel. So you have 10. Now you have of the order of 10 or 150 or so. Now quantum mechanics would say no pattern in your room if Planck's constant would be a million billion times more large. So if you see in your room a fixed pattern, even if Planck's constant were large, that means for a small number fixed pattern, that is a violation of quantum mechanics. Now here I leave this lecture because, as I said, that's just a logical discussion. An actual experiment, this is not our world. For our world, you have to wait for the next lecture. And for that, first I summarize. And the summary has nothing new. Again and again I have said that a visible sign of probability and quantum mechanics is, so far I have told you quantum mechanics is only probability. Quantum mechanics has other results as well. But so far I have told you only probability. And for that much, if you have to wait a visible sign, then the experimental test, observational test, then you see for a large number you have a pattern, for a small number no pattern. This combination is signature of quantum mechanics and classical mechanics. Now, this combination is a signature of quantum mechanics. Now the topic starts, although this is only a start and end is the next lecture. What is the difference between classical mechanics and quantum mechanics? The difference is for a small number of repetition. For small number, classical mechanics was a pattern and quantum mechanics no pattern. Now how to do that in our world where Planck's constant is what it is? That is an experimental arrangement, which is the topic of next lecture, which is a famous double slit experiment. So to remain aware to that, simplest is that you should subscribe to this channel so that you remain aware of this and whatever comes next.